At 8:40 in the morning, Mountain Daylight Time today, the National Weather Service issued a blizzard warning along Interstate 80 in Wyoming. 3 hours later, in Boston, the same agency wrote that 850 millibar temperatures on Tuesday would be 2 to 3 standard deviations above the operational climate record, close to the maximum relative to climatology for this time of year. A blizzard warning and an all-time May heat record forecast issued by the same agency on the same calendar day. 404 active alerts are in force across the country. 5 categorical operational extremes are running simultaneously, and every one of them is being driven by a single Rossby wave that has amplified into a configuration the climate model said should not be this common, this early in the year. The framing on social media this morning is calling it convergence. The framing in the peer-reviewed literature has a different name. We are going to walk through what the wave actually is, why it is producing the snow and the heat on the same day, what loaded the gun, and what the next configuration looks like, including the part nobody is talking about, which is why this kind of day is going to keep happening. If you have been watching the patterns this channel has been tracking for the last months, today is the verification. Subscribe to the Sky Lab for what comes after this wave breaks, because the next one is already in the data and we will be ready when it arrives. Drop a comment with where you're watching from, and whether you are under the heat side of the wave or the snow side. Now, let's get into it. Part 1. The day. The atmosphere refused to pick a season. At 8:40 in the morning Mountain Daylight Time on Monday, May 18th, 2026, the National Weather Service office in Cheyenne, Wyoming issued a blizzard warning. The warning covers the North Snowy Range foothills along Interstate 80, including Arlington and Elk Mountain. The text says that blizzard conditions are currently occurring. Winds are gusting to 50 miles per hour. Visibilities are dropping below a quarter mile due to falling and blowing snow. The severity classification on the alert is extreme. That is the highest urgency tier the National Weather Service uses for winter storm products. The warning runs until 3 in the afternoon. The state of Wyoming has 31 active alerts on its books today, which is the highest of any state in the lower 48 outside of marine zones. 3 hours earlier, at 5:32 in the morning, Mountain Daylight Time, the same upper trough that is producing the Wyoming blizzard, was being analysed by forecasters at the Denver Boulder office. They wrote that the trough is going to ride across the state through the afternoon and produce widespread precipitation. East-facing slopes north of Interstate 70 and the mountains are expected to see 12 to 18 inches of snow. Rocky Mountain National Park was upgraded to a winter storm warning. The Snowy Range was upgraded to a winter storm warning. The North Laramie Range was upgraded to a winter storm warning. The Sierra Madre Range was upgraded to a winter storm warning. The Ferris, Seminole, and Shirley Mountains were upgraded to a winter storm warning. South Laramie Range, Central Carbon County, the entire Wyoming high country, all in winter storm mode at the same time. At 7:30 in the morning, Eastern Daylight Time, while the Wyoming snow was already falling, the National Weather Service office in Boston, Norton, Massachusetts, was writing the morning area forecast discussion. The key message at the top of that discussion contained this language: increasing confidence of record heat Tuesday for parts of southern New England. Then, further down, the office wrote this: an anomalous upper-level ridge builds over the region Tuesday with rather warm low-level temps. 850 millibar temps are 2 to 3 standard deviations above normal, which is close to the maximum relative to the CFSR climatology for this time of year, suggesting very anomalous heat. Pause for a second on that sentence, because it is the sentence that this entire video turns on. A National Weather Service forecaster, writing the morning office discussion for southern New England, is describing the temperatures at 8,500 feet of atmosphere as approaching the maximum relative to the operational climate record for this time of year. The climate record they are using is called the Climate Forecast System Reanalysis, which goes back to 1979. That is 46 years of operational meteorological data. The Boston office, in the most measured, technical, operational language that the National Weather Service uses, just told their forecast audience that what is about to happen Tuesday is approaching the worst-case scenario in the modern record for this date. And on the same morning, with the same set of weather products issuing from offices in the same agency, a blizzard warning is in force in Wyoming, an extreme heat anomaly is being staged for southern New England, A moderate risk for severe thunderstorms has been posted by the Storm Prediction Center for parts of Kansas, Nebraska, and Missouri. A fire weather risk at the extreme tier, the highest non-special emergency designation the Storm Prediction Center uses, is in force for the southern high plains, and a moderate risk for flash flooding has been posted by the Weather Prediction Center for central Missouri. All 5 of those operational extremes are on the same calendar day. All 5 are operating in the same 24 hours. All 5 are being produced by the same single Rossby wave that is currently amplified across the continent. 404 active alerts are in force on this date. That is the total count from the National Weather Service for this morning. 404 products in force at the same time. The mix of them, and pay attention to this list, because this list is the actual story of the day, includes 1 blizzard warning, 12 winter storm warnings, 19 winter weather advisories, 7 freeze warnings, 6 freeze watches, 15 red flag warnings, 1 fire weather watch, 1 heat advisory with more building behind it through the afternoon, 21 flood warnings, 10 flood watches, 3 severe thunderstorm warnings, 6 severe thunderstorm watches, 16 wind advisories, 19 gale warnings, 27 air quality alerts. Every season of the year is represented in those products: winter products, severe weather products, fire weather products, flood products, heat products, marine products. The National Weather Service has run out of seasons to issue products against. The entire annual rotation is active simultaneously. This is not a normal day, and what makes it especially not a normal day is that all 404 of those alerts are being driven by one piece of physics. There is one deep upper-level trough, currently digging into the Great Basin and ejecting energy out of the Rockies. There is one anomalously strong high-pressure feature, a Bermuda high, anchored offshore the eastern seaboard. The trough and the high are mechanically coupled. They are 2 halves of the same wave. The wave has amplified. The amplification is what is producing the simultaneity. Down at the Weather Prediction Center in College Park, Maryland, the 8:30 in the morning Coordinated Universal Time discussion was written by a forecaster named Kong. Kong's discussion, which is the document that flows out to local National Weather Service offices and to the broadcast meteorology community, has 4 key messages at the top. The first one says, another day of active severe weather and flash flood threat across the east-central US before shifting south into the southern plains late Tuesday. The second says, extreme fire weather concerns across the southern high plains today. The third says, heavy wet snow blankets the higher elevations of Wyoming, the Front Range, and the Wasatch before tapering off tonight. The fourth says, an early season heat wave will challenge temperature records across the eastern US. That is the entire weather story of the country, in 4 sentences written before sunrise on the East Coast. The state-by-state alert distribution is its own diagnostic. Wyoming is sitting on 31, Missouri is at 29, Kansas is at 22, Texas is at 16, California is at 14, Colorado is at 13, Illinois is at 9, New Mexico is at 8, New Jersey is at 8, New York is at 7, Connecticut is at 7, Florida is at 6. Oklahoma is at 6. There is no part of the country where nothing is happening. The eastern third has heat advisories building. The middle third has tornado watches and flood warnings. The western third has blizzard warnings and red flag warnings. The corners have rip current statements and small craft advisories. Every operational meteorologist in the lower 48 is busy this morning. Here is what is uncomfortable about putting all of that on the same paragraph. There are no surprises in any individual piece. A moderate risk severe weather day in mid-May in Kansas is not strange. A late-season snow event in the high Wyoming mountains is unusual, but not unheard of. An early-season heat wave on the East Coast happens roughly once a decade. A fire weather concern in the Texas Panhandle in May after a drought year is normal. A flash flood moderate risk in central Missouri is consistent with the saturated soils that have been there for weeks. Each of these stories on their own would barely make a national broadcast. The story is the simultaneity. The story is the fact that they are all happening at once, driven by one configuration on the same calendar date. And the office that has written that down most carefully, in the most technical language, with the least amount of editorial heat, is Boston, because Boston is the one looking at numbers that are close to the maximum relative to the operational climate record for this date. So that is where we are going next. We are going to look at the Boston number. We are going to look at what 2 to 3 standard deviations means against a 46-year reanalysis baseline. we are going to translate 850 millibar temperatures of 18 to 20 degrees Celsius and 925 millibar temperatures of 24 to 26 degrees Celsius into the actual numbers that will appear on thermometers from DC to Manchester, New Hampshire Tuesday afternoon. And we are going to look at what the heat risk scale's major designation means for a region that has not had major heat risk in May in a long time. Because if Boston is the office writing close to the maximum relative to climatology, the 404 alerts and the blizzard warning and the tornado outbreak are not the headline number. The Boston number is the headline. Part 2. The Boston 850 millibar anomaly. The Climate Forecast System, reanalysis, abbreviated as CFSR, is one of the operational climate datasets that the National Weather Service uses as its baseline for atmospheric anomalies. CFSR covers the period from January 1st, 1979 to the present. It is updated continuously. It contains gridded data for temperature, wind, humidity, geopotential height, and dozens of other variables at standard pressure levels from the surface all the way up to the top of the atmosphere. The pressure level that matters for what Boston is forecasting Tuesday is 850 millibars. 850 millibars is approximately 5,000 feet above sea level. The temperature at that pressure level is the temperature of the lower troposphere, the part of the atmosphere that mixes down to the surface during the day when the sun heats the ground. When a forecaster at the Boston office writes that 850 millibar temperatures Tuesday will be 2 to 3 standard deviations above the CFSR climatology for this date, they are saying something very specific. They are taking the forecast model output for Tuesday morning, looking at the modelled 850 millibar temperature, comparing that temperature to the distribution of all 850 millibar temperatures recorded in the reanalysis for the same calendar date across the 46-year baseline, and reporting the standardized departure. 2 standard deviations above the mean places that value in roughly the top 2.3% of all observations in the historical record. 3 standard deviations places it in roughly the top 0.13%, about 1 in 750 observations. The forecast is for the lower bound of a 2 sigma anomaly and the upper bound of a 3 sigma anomaly. In a 46-year record, 3 sigma events happen on the order of once a decade, sometimes less. 2 sigma events are not common, but they are not vanishingly rare. The detail that pushes this past statistical curiosity is the language Boston used after the number. They wrote that this is close to the maximum relative to CFSR climatology for this time of year. That is the operational interpretation. The number is approaching the highest value the reanalysis has ever recorded for this date in southern New England. Forecasters at National Weather Service offices do not write that lightly. They are professional meteorologists looking at operational model output and comparing it to a 46-year benchmark. When they say close to the maximum, they are signalling that we are inside the tail of the distribution that the audience has not personally experienced. What does an 850 millibar temperature of 18 to 20 degrees Celsius actually mean at the ground? Translate it. 18 degrees Celsius is 64.4 degrees Fahrenheit. 20 degrees Celsius is 68 degrees Fahrenheit. So the temperature at 5,000 feet above southern New England Tuesday afternoon is going to be in the mid-60s Fahrenheit. That is the air mass arriving over the region. When that air mass mixes down to the surface, it gets compressed adiabatically as it descends, which warms it by about 10 degrees Celsius per kilometre of descent, or roughly 5.5 degrees Fahrenheit per 1,000 feet. From 5,000 feet down to the surface, that is approximately 27 degrees Fahrenheit of warming as the air column mixes. Add that to a 64 to 68 degree starting point at altitude, and you get surface temperatures in the lower 90s at the cool end and approaching the lower hundreds at the warm end. Boston specifies that the actual forecast is mid-90s, away from the south coast, with potential for some upper 90s in the Connecticut River Valley. That is consistent with the 850 millibar number. The science is internally consistent and is telling the office what to expect. The 925 millibar forecast is even more diagnostic. 925 millibars is about 2,500 feet above sea level. The forecast for Tuesday is 24 to 26 degrees Celsius. That is 75 to 79 degrees Fahrenheit at 2,500 feet. When that mixes down to the surface, you get temperatures into the mid to upper 90s, without much further warming required. The two pressure levels are telling the same story. The lower troposphere is hot. The boundary layer is going to be hot. The mixing is going to be efficient because the air is dry. The dew points are forecast in the low to mid-60s, uncomfortable but not catastrophic from a heat index perspective, which means the air temperature itself is what will be doing the damage. The Mount Holly office in New Jersey, which covers the urban corridor through Philadelphia, Atlantic City, and the inland Pennsylvania, New Jersey, Delaware, Maryland region, framed Tuesday similarly. Their morning discussion at 6:19 a.m. Eastern Daylight Time contained this language. Unusual and potentially record-setting, early season heat is expected through Wednesday. High temperatures will generally be upward of 10 to 20 degrees above normal, with low to mid-90s expected for many areas today through Wednesday. They started the heat advisory at noon today for the Pennsylvania and New Jersey urban corridor. They explicitly noted that temperatures and heat indices will likely be hotter on Tuesday. The dew points will mix out a bit during the afternoon, which is the technical reason that heat indices will run close to air temperatures, not far above them. But the air temperatures themselves are doing the work. Then the Mount Holly discussion contained a sentence that is worth pulling out for what it tells us about the public health side. The forecast says, not terribly humid, but certainly uncomfortable since we aren't acclimated to it yet. There is a clinical reason that early season heat events are operationally dangerous in ways that midsummer heat events are not. The human body acclimates to heat over the course of several weeks of repeated exposure. Sweat rates increase. Sweat composition changes to conserve electrolytes. Plasma volume expands. The cardiovascular system adapts to handle higher skin blood flow. None of those adaptations have happened yet in southern New England, in eastern Pennsylvania, in northern New Jersey, or in the New York metropolitan area, because the region has been in the 60s and 70s until this past weekend. The first heat event of the season, the one the Boston office explicitly labelled "This is our first heat of the season," kills more people, per degree of departure from normal, than the 7th or 8th event of the season. The acclimatization curve takes 10 to 14 days. There has not been 10 to 14 days. There has been the weekend. The Baltimore and Washington office, which covers the D.C. area, Central Virginia, and the Maryland-Delaware urban corridor, was even more direct in its Monday morning discussion. They wrote, Key Message 1, near-record warmth with isolated strong to severe thunderstorms over the mountains today and Tuesday. They went on to describe the forecast as marking one of the hottest days so far this season, although even hotter conditions can be expected Tuesday as the upper-level ridge peaks over the region. Their Tuesday forecast says highs well into the low to mid-90s. A few upper 90s cannot be ruled out across the urban corridor and down to the south across the central Virginia Piedmont, given the strengthened ridge peaking overhead and dry air at the surface. So DC is going to be in the mid to upper 90s Tuesday. Richmond is going to be in the upper 90s, Hagerstown, Frederick, Cumberland, all in the mid-90s. The New York City office, which covers Central Park Station observations, and the New York, Long Island, Connecticut metropolitan area, framed Tuesday and Wednesday in their morning discussion as summer-like temperatures through Wednesday. Their forecast high for Central Park on Wednesday is 94 degrees Fahrenheit. They specifically noted that guidance often has a tough time getting hot enough in vicinity of a front, especially a few days out, and that despite that bias, the model blend still has a 94 for Central Park on Wednesday. In other words, the model has a known low bias for situations like this one. The actual surface temperature is likely to come in at the warm end of the forecast range, or even slightly above it. Central Park's all-time May daily record is, depending on the date, somewhere between 96 and 99 degrees. 94 degrees challenges the upper end of the climatological distribution, but is unlikely to break the daily record at Central Park itself. It will, however, almost certainly produce all-time monthly records at several smaller stations across the region. The kind of stations that have been recording temperatures for 150 years, and that have never seen the upper 90s on a May date. This brings us to the heat risk scale. The heat risk scale is a product that the National Weather Service has been operationally developing for several years. It is a 5-level scale, minor, moderate, major, extreme, and a top tier, that combines temperature, time of year, day-night heat continuity, and historical heat-related mortality and morbidity data into a single risk score for a given location and date. The major designation is the 3rd tier from the bottom. It is reserved for events with elevated mortality and morbidity potential, especially for sensitive populations and unacclimatized people. The current National Weather Service heat risk forecast for Tuesday Across the mid-Atlantic and southern New England is major. That includes Washington, Baltimore, Philadelphia, New York City, Hartford, Boston, and the inland corridors of all of those metros. May major heat risk in the Northeast is operationally early. The historical distribution of major heat risk designations in this region clusters from late June through August. May major heat risk happens in this region every 5 to 10 years on average, depending on the office and the threshold. Tomorrow is going to be one of those rare days. Wednesday may continue the run before the cold front arrives, Wednesday afternoon, and breaks the pattern. 2 days of major heat risk in May, in a region that has not had it on the calendar yet this year, is the public health side of the simultaneity story. The hospitals know this is coming, the cooling centres are being staffed, the emergency management agencies are pre-positioning, and the broadcast meteorologists are about to have an extremely loud 48 hours. And here is the part that most people watching their local TV broadcast tonight will not hear. Boston is the office writing close to the maximum relative to CFSR climatology. The forecast value for 850 millibars Tuesday is 2 to 3 standard deviations above a 46-year reanalysis baseline. The number is in the tail of the historical distribution. The wave that is producing the number is the same wave that put a blizzard warning over Interstate 80 in Wyoming this morning. The number is not in southern New England by accident. The number is there because a Rossby wave on the eastern side of the continent has amplified to an extent that the office issuing the forecast is reaching for the strongest language the operational vocabulary allows. And if Boston is the office writing close to the maximum relative to climatology, you might think the rest of this story is the rest of the East Coast, the cities, the heat advisories, the records about to fall. It isn't. The rest of this story is on the other end of the country. The rest of this story is in Wyoming. Part 3. The Wyoming side of the wave. The North Snowy Range foothills sit along Interstate 80 between the towns of Arlington and Elk Mountain in south-central Wyoming. The elevation along that stretch of I-80 runs between 6,500 feet and 8,000 feet. The road climbs over a pass that has been the site of more lethal winter storm crashes over the last 50 years than almost any other stretch of interstate in the United States. The locals refer to that section of the road as the Snowy Range Corridor. It is closed by the Wyoming Department of Transportation, an average of 50 to 70 days a year due to weather. It is closed today. The National Weather Service office in Cheyenne issued the blizzard warning for that stretch at 8:40 in the morning, Mountain Daylight Time. The text is short and operational. Blizzard conditions currently occurring along the 80 in the North Snowy Range foothills. Additional snow accumulations between 2 and 6 inches. Winds gusting as high as 50 miles per hour. Visibilities may drop below 1/4 mile due to falling and blowing snow. The warning runs until 3 in the afternoon. The severity tag on the alert in the operational metadata is extreme. Stacked behind the blizzard warning are 5 separate winter storm warnings issued by the same office for the same date. The Sierra Madre Range is expecting 8 to 16 inches of total snow accumulation, with winds gusting to 50 miles per hour, periods of blowing and drifting snow, mainly on the eastern side of the range. The Snowy Range itself and the North Laramie Range, which is the higher elevation extension to the south, are expecting 10 to 20 inches with locally higher amounts possible, winds gusting to 30 to 40 miles per hour, blowing and drifting snow especially above 8,500 feet. The Ferris, Seminole, and Shirley Mountains are expecting 6 to 12 inches with higher amounts near the mountains, winds gusting to 35 to 45 miles per hour. Central Carbon County is expecting 5 to 10 inches with locally higher amounts near the mountains, winds gusting to 45 miles per hour. The South Laramie Range, including the Interstate 80 summit between Cheyenne and Laramie, is expecting 7 to 14 inches with locally higher amounts, winds gusting to 30 to 40 miles per hour. Add it up, 1 blizzard warning, 5 winter storm warnings stacked behind it, all from the same National Weather Service office, all on the same date, all in effect today and ending this evening. And out east of the Wyoming high country in Colorado, the National Weather Service Denver office has upgraded the foothills above 8,000 feet to a winter storm warning of its own. East-facing slopes north of Interstate 70, in the mountains of Rocky Mountain National Park and the Medicine Bow Range, are forecast to receive 12 to 18 inches of snow today. Lower foothills below 8,000 feet will get 4 to 8 inches. This is not the only winter storm warning in the country today. There are 12 total in force. There are 19 winter weather advisories in force as well, which is a lower severity tier covering smaller snow totals or more transient conditions. 31 winter weather products are active in the middle of May across Wyoming, Colorado, parts of Utah, and the northern high country. The blizzard warning is the one that the metadata flags as extreme. The criteria for a blizzard warning in the operational definition that the National Weather Service uses are these. First, sustained winds or frequent gusts must be at 35 miles per hour or greater. Second, falling or blowing snow must frequently reduce visibility to under 1/4 mile. Third, those conditions must continue for at least 3 consecutive hours. The North Snowy Range Foothills event meets all 3 criteria. Winds are gusting to 50 miles per hour. Visibility is dropping below 1/4 mile in the falling and blowing snow. The conditions are occurring continuously through the morning into the afternoon. By definition, this is a blizzard. Issued in mid-May, in the lower 48. This is statistically rare. Mid-May blizzard warnings in the lower 48 are not unprecedented. May 2017 produced a notable case in eastern Wyoming and the western Nebraska panhandle that closed major roads for 2 days, but they are uncommon. The climatological window for blizzard warnings in the high Wyoming country runs from October through April. May blizzard warnings happen, but they are events that long-term residents remember. They are anomalies, and they tend to happen when a deep upper-level trough that should have been gone weeks ago decides to dig back down out of the Pacific Northwest into the Great Basin and the Central Rockies, and runs cold air down the backside at the same time that the eastern half of the continent is heating up. That is exactly what is happening today. The Denver Boulder office spelled out the mechanism in their morning area forecast discussion. The trough over the Great Basin is moving across the area Monday with favourable mid-level ascent through the afternoon hours. At the surface, upslope flow is in place. Upslope means the wind is blowing from east to west, into the rising terrain of the Front Range. Air that is forced upward cools adiabatically, about 10 degrees Celsius per kilometre of lift. As it cools, it reaches saturation. As it saturates, it precipitates. If the temperature at the elevation where it precipitates is below freezing, it precipitates as snow. The east-facing slopes of the Front Range and the Medicine Bow Range are forced uplift zones in this configuration. When the trough is digging deep enough and the upslope flow is moist enough, you get the kind of accumulations we're getting today, 12 to 18 inches on the east-facing slopes north of Interstate 70. The same air mass that is precipitating snow on the east-facing slopes of the Rockies is producing the blizzard conditions along I-80 and the North Snowy Range. Strong westerly winds are blowing down the backside of the higher terrain. Where the terrain channels those winds, and the I-80 corridor through Arlington and Elk Mountain is the most reliable wind channel in the entire Rocky Mountain West, you get gusts of 50 miles per hour. The falling snow gets caught in those gusts. The visibility collapses. The roads close. People who tried to drive across that stretch this morning are sitting in vehicles waiting for the warning to expire at 3 in the afternoon. The Sierra Madre Range component of the system deserves a separate mention because of the magnitude. 8 to 16 inches of total snow accumulation, mainly on the eastern side, in the 3rd week of May, is a lot of snow. The Sierra Madres are the lower elevation range west of the Snowy Range proper. Their climatology for May, averaged across the period of record, has them receiving on the order of 2 to 4 inches of snow during the entire month. Today, they are getting 8 to 16 inches in a single 12-hour event. The North Laramie Range, which has higher elevation peaks and a higher snow climatology, has a May average closer to 6 to 8 inches across the entire month. Today they are getting 10 to 20 inches. The Medicine Bow Range, which the National Weather Service Denver office specifically called out in their warning text, has a similar climatology and is getting 12 to 18 inches today. This kind of snow event at this point in the calendar sets up the secondary effects that the National Weather Service does not put on the alert page, but that anyone who lives in the area can see immediately. The snow line is dropping to about 7,500 feet during the heaviest precipitation today. Below that line, the precipitation is falling as cold rain, which is saturating already saturated ground. The spring runoff timing, which has been ahead of climatology this year because of the warm April, just got reset. Late season heavy wet snow on top of already melting snowpack can produce abrupt secondary runoff pulses when it melts off. Crews are watching the Cache La Poudre and the North Platte drainages for what happens over the next 48 hours. Wyoming has 31 active alerts today, and that is the highest single-state count in the lower 48 outside of the marine zones. The mix includes the blizzard warning, the 5 winter storm warnings, multiple winter weather advisories, wind advisories along the corridors that are not in the blizzard warning area, and the freeze watches that come into force tonight as the cold air settles into the lower valleys. Cheyenne itself is forecast to drop into the upper 20s to low 30s Monday night. Casper is forecast to drop into the mid-20s. The state is in winter in the morning of May 18th, with operational alerts that the National Weather Service has issued because the conditions warrant them. And here is the part that is important to fix in your head before we move on. The trough that is digging into Wyoming and producing the blizzard is the same trough that is ejecting waves out of the Rockies into the Central Plains and producing the moderate risk tornado outbreak in Kansas and Nebraska. The trough is the western half of a single Rossby wave that runs from the Pacific Northwest all the way across the continent to the western Atlantic. The eastern half of that same wave is the ridge that is anchoring the Bermuda High in place offshore the east coast. The eastern half of the wave is what is making the Boston 850 millibar temperature 2 to 3 standard deviations above CFSR climatology Tuesday. The same wave is doing both things at the same time. It is amplified. The Wyoming blizzard and the New England heat dome are two faces of one configuration. They are not coincidences. They are not separate stories. They are mechanical consequences of the same piece of atmospheric physics, on opposite ends of a wave that is currently locked into a high-amplitude, low-phase speed resonance that has been the subject of climate science papers for the last 5 years. So this is where the question gets uncomfortable, because if the same wave is doing both of these things at the same time, you have to ask what the wave is, and what the wave is a piece of physics that is happening more often, with greater amplitude, and earlier in the year than the model said it would. The papers that describe this configuration in the technical literature are not telling a comforting story. They are telling a story about the atmosphere learning a new behaviour, and the new behaviour is exactly what we are watching happen on the morning of May 18th, 2026. Part 4. One wave, two faces. A Rossby wave is a planetary-scale undulation in the mid-latitude westerly winds. They are named after the Swedish-American meteorologist Carl Gustaf Rossby, who described their basic dynamics in a paper published in 1939. The physical mechanism behind them is the combination of two things. The first is the Coriolis effect, the apparent deflection that anything moving in a rotating reference frame experiences. The Earth rotates from west to east, and any parcel of air moving across the surface of the Earth gets deflected to the right in the northern hemisphere and to the left in the southern hemisphere because of that rotation. The second is the temperature gradient between the equator and the pole. The equator is warm, the pole is cold. Warm air over the equator wants to rise. Cold air over the pole wants to sink. Air gets transported from one to the other to keep the system balanced. Put those two things together, a deflecting Coriolis force, acting on air that is being transported between two reservoirs at different temperatures, and you get the mid-latitude westerly winds. Air aloft, between roughly 30 degrees and 60 degrees latitude in either hemisphere, blows from west to east in a band that wraps the planet. That band is not straight, it undulates. The undulations are Rossby waves. They have wavelengths on the order of 3,000 to 6,000 kilometers, depending on the temperature gradient and the latitude. They have amplitudes that can range from a few hundred kilometers in their suppressed state to a couple of thousand kilometers in their amplified state. And they have a phase speed, the speed at which the entire wave pattern moves eastward. That is typically around 15 degrees of longitude per day in their normal state. That means the entire global wave pattern progresses eastward by about the distance from Boston to Detroit each day. In their normal state, Rossby waves do their job quietly. They mix warm and cold air. They produce day-to-day weather. They keep cold polar air bottled up at higher latitudes most of the time. They occasionally let cold air spill south in winter or warm air spill north in summer. Forecasters track them on 500 millibar charts, which is the pressure level at about 18,000 feet where the wave structure is clearest. You can see the troughs and ridges as dips and bulges in the wind pattern. Then sometimes, and the conditions that make this happen are the subject of an active field of climate research, the waves stop being modest. They amplify. The dips dig farther south. The bulges build farther north. The phase speed slows down. The pattern, instead of progressing eastward at 15 degrees per day, slows to 5 or 3 or even close to 0. The wave gets locked in. The same regions sit under the same troughs and the same ridges for days at a time, and the consequences are what we are watching happen today. The technical name for this in the recent climate literature is quasi-resonant amplification. The concept dates back to a paper by Vladimir Petukov and colleagues in 2013, published in the Proceedings of the National Academy of Sciences. Petukov and his collaborators found that when waves of a specific wavelength get trapped in the mid-latitudes, when their natural eastward propagation is interrupted by boundary conditions in the polar jet, they enter a resonance condition where they can no longer move and their amplitude grows. The specific wave numbers that this happens to are wave numbers 6, 7 and 8. Wave number 6 means 6 full ridge trough cycles around the hemisphere. Wave number 7 means 7. Wave number 8 means 8. When the waves are at one of those numbers, and the conditions in the polar jet are right, they get stuck. The Petukov paper was a starting point. The field has developed substantially since then. The most important follow-up from the perspective of what we are watching today is a 2020 paper in Nature Climate Change by Kai Kornhuber, Daniel Kumu, and a team of climate scientists across several institutions. The title of the paper is Amplified Rossby Waves Enhance Risk of Concurrent Heat Waves in Major Breadbasket Regions. The paper looked at the historical record of concurrent heat extremes in the Northern Hemisphere, the kinds of events where 2 or more major agricultural regions experience extreme heat at the same time, separated by thousands of kilometres, while the rest of the hemisphere is at or near climatological normal. They found that when the planetary wave was at wave number 5 or wave number 7, the probability of concurrent extremes increased by up to a factor of 20. That is not a typo, 20 times more likely. The cascading effects on crop yields were quantified as about a 4% average global reduction in major crop production, with regional reductions of up to 11% during the worst wave number 5 and wave number 7 years. The dynamical mechanism that the Kornhuber paper described is the same one that is operating today. When the wave gets locked into a high-amplitude, low-phase speed configuration, the regions sitting under the persistent ridges experience persistent high pressure. Persistent high pressure means descending air. Descending air means clear skies, low humidity, and strong solar heating. After 3 or 4 days of that, the surface is hot. After 5 or 6 days, the surface is very hot. After a week, you are setting records, and the configuration does not break by itself. It has to be broken by a change in the upstream forcing, which usually comes from the tropics in the form of a Madden-Julian oscillation propagating eastward through the Pacific, or from a shift in the North Atlantic storm track, or from a stratospheric sudden warming event that disrupts the polar vortex. That is the eastern ridge side of the wave. The opposite end of the same wave is also locked in. The western trough is anchored against the cold air pool to its north and the warm air pool to its south. The temperature gradient across the trough is what is doing the energy work that maintains the storm pattern in the central plains. The mechanical coupling between the trough and the ridge, the fact that they are 2 faces of one wave, is what makes them persist together. If you break the ridge, you break the wave, and the trough goes too. If you break the trough, you break the wave, and the ridge goes too. They have to be broken together. The current configuration matches the wave number 5 to wave number 7 signature that the Kornhuber paper identified as the highest risk pattern for concurrent extremes. The wave is locked, the phase speed is low, the amplitude is high, the trough is over the Great Basin, the ridge is over the Western Atlantic, the Mid-Pacific has its own ridge, the Western Pacific has its own trough, and the pattern around the hemisphere looks like a roughly 5 to 7 count of stationary highs and lows. That is the resonance signature, and the resonance signature is what is producing the simultaneity of the Wyoming blizzard and the New England heat dome. There is a second paper that is worth bringing in here, because it goes after the persistence question specifically. It is a 2021 paper in Water Resources Research by a team that included Wonsun Han. The title is on low phase speed Rossby wave packets and persistent drought in the western United States. The paper looked at the historical relationship between slow-moving Rossby wave packets and the location and duration of regional droughts. The finding was that low-phase speed packets are statistically associated with persistent regional drought, because slow-moving high-pressure features sit over the same regions for weeks and prevent precipitation systems from reaching them. The mechanism is the same one we're watching. The Bermuda High that is currently anchoring the eastern ridge in place is a low phase speed feature. It is sitting offshore the east coast and not moving. It is trapping warm continental tropical air over the east coast. It is doing what the Han paper said low phase speed features do. And then there is the part of the literature that is harder to talk about, because it is the part that says these patterns are happening more often than the climate model said they would. There is a follow-up paper from Kornhuber and others in 2023 published in Nature Communications. The title is Risks of Synchronized Low Yields are Underestimated in Climate and Crop Model Projections. The argument in the paper is that the models that project future climate, the CMIP6 suite, which is the current generation of coupled atmosphere ocean models used in IPCC assessments, do not adequately reproduce the resonance behavior that produces these concurrent extreme events. The reason is that the models have some structural biases in how they represent the upper-level jet stream. They tend to be slightly too zonal, too west to east, and not amplify the waves enough. When you compare model output to observations over the recent decades, the observations show more amplification and more synchronized extremes than the models predicted. The implication of the Kornhuber 2023 paper is that we are probably underestimating the future frequency and intensity of this kind of day. The models say events like today should happen with some calculable frequency. The observations are saying they happen more often than that, which means the climate of the next 20 years is probably going to contain more days like today than the projections show. Whether that is 1 extra event per decade or 5 extra events per decade depends on the magnitude of the model bias and the climate scenario, and neither of those is settled. But the direction is settled. The models are under-predicting. You can stack the science up next to what is happening on the screen. The wave is at the wave number range that Petukov said gets stuck. The amplitude is in the range that Kornhuber said produces 20-fold concurrent extreme risk. The phase speed is low in the way that Han said produces persistent regional anomalies. The events on the surface, the blizzard, the heat dome, the tornado outbreak, the fire weather, are the concurrent extremes that the literature said this configuration produces. And the frequency of this configuration is, per the Kornhuber 2023 follow-up, probably underestimated in the models that are being used to project what the next 20 years look like. This is what people miss when they talk about a heat wave as a single anomaly. Today's event is not a heat wave. Today's event is a configuration. The configuration is producing the heat wave on one face, the blizzard on the opposite face, the tornado outbreak on the eastern flank of the trough, and the extreme fire weather on the descending air on the backside of the trough, where the dry air is flowing into the southern Rockies. The configuration is producing all 4 faces at the same time, because they are all faces of the same wave. And the wave is in a state that climate science has been describing in increasingly precise language for the last 12 years. The state has a name, it has a wave number signature, it has a statistical fingerprint, it has been linked, in peer-reviewed papers, to crop failures, drought, and concurrent heat extremes. The pattern is not coming out of nowhere. The pattern is exactly what the literature said this kind of pattern looks like, and the wave did not amplify in a vacuum. It amplified into preconditions that have been building for months. Which is the part of the story we're going to look at next, because if the amplification is the trigger, the preconditions are what loaded the gun. Part 5. How the drought loaded the heat dome. The first precondition is what we covered in our video from May 12th, the worst spring drought on the modern instrumental record across the United States. The National Centers for Environmental Information Climate Division dataset goes back to 1895. That is 131 years of operational climate observation. The January through April 2026 period was the second driest in that entire record, behind 1910. The Palmer Drought Severity Index for March 2026 was minus 7.85. The April value was minus 7.56. The only months in the entire record that recorded lower PDSI values are July and August of 1934, the bottom of the Dust Bowl. 43.8% of the lower 48 was in D2 or worse drought by late April, which is the largest footprint since August 2012. 44% of the contiguous United States was rated D1 or worse by May 5th. The Florida drought specifically peaked at 99% state coverage in late April, with 78% in D3 and 22% in D4, the most intense drought footprint in Florida's 15-year monitoring history. This is the loaded gun. The dry land surface, across more than half the country, is the backdrop against which the eastern ridge is building today. And the reason that backdrop matters for the heat dome is a piece of physics that gets a paragraph in atmospheric science textbooks, but does not usually make it into broadcast meteorology. It is called soil moisture-atmosphere coupling. The pathway was quantified in a 2019 paper in the Proceedings of the National Academy of Sciences by a team that included Diego Morales at Ghent University. The Morales paper found that under dry land surface conditions, the likelihood of extreme heat increased by about 30% compared to wetland surface conditions, with the largest effect during transition seasons like spring and early summer. The physics behind the effect is straightforward once you see it. When the sun is shining on the surface of the Earth, the incoming radiation has to go somewhere. Some of it gets reflected back into space. That is the surface albedo, the brightness of the surface, which depends on what the surface is made of. The rest of it gets absorbed by the surface, which means it has to be released back to the atmosphere somehow. There are two main pathways that the surface uses to release energy. One is called sensible heat. The surface just gets hot, and it warms the air directly through contact and conduction. The other is called latent heat. Water on the surface evaporates, which takes a tremendous amount of energy with it as the water transitions from liquid to vapor. Evaporating a kilogram of water requires about 2.5 million joules of energy. That energy comes out of the surface and goes into the atmosphere as latent heat in the water vapor, not as sensible heat in the air temperature. What this means is that the partitioning of incoming solar energy between sensible heating and latent heating is determined by how much water is available at the surface to evaporate. When the surface is wet soil, transpiring plants, lakes, rivers, most of the incoming energy goes into latent heat. The air stays cooler. The temperatures over a wet land surface during a heat wave are typically several degrees cooler than they would be over a dry land surface with the same solar input. When the surface is dry, there is no water available to evaporate. All of the incoming energy has to come out as sensible heat. The air gets very hot. The temperatures spike. This is why the Dust Bowl summers of 1934 and 1936 were so brutal. The Great Plains had no moisture to evaporate. The incoming solar radiation went entirely into heating the air. The combination of high pressure aloft, dry surface below, and persistent ridging produced surface temperatures that broke state heat records that have never been broken since. The Cook, Miller and Seeger paper from 2009 in PNAS quantified this. The Dust Bowl heat wave amplification was substantially driven by the dry land surface, with a contribution from land degradation and dust aerosol that was on the order of 1 degree to 1.5 degrees Celsius of additional warming above what the synoptic pattern alone would have produced. The mechanism that amplified the Dust Bowl heat is the mechanism that is amplifying the eastern heat dome today. The drought across the southwest, the southern plains, and the southeast over the last 6 months has produced a continental-scale dryland surface. The soil moisture across the entire region is in the bottom 10th percentile of historical values for the date. The transition from wetland to dryland for a heat dome of given strength is, per Morales 2019, on the order of 30% additional likelihood of extreme heat. That 30% extra likelihood is part of why Boston is forecasting 2 to 3 standard deviation 850 millibar anomalies tomorrow. The ridge would have built either way. The dry land surface is what is making the surface temperatures under the ridge as high as they are. That is the first precondition. The second precondition is more recent. It is the aerosol unmasking pulse that began in 2020. In January of 2020, the International Maritime Organization implemented a new global sulfur cap on marine fuel, the IMO 2020 regulation. Before 2020, ocean shipping was running on bunker fuel with sulfur content around 3.5%. After 2020, the cap dropped that to 0.5%. The change reduced sulfate aerosol emissions over the global oceans, particularly over the North Atlantic shipping lanes, by roughly 1/3 overnight. Sulfate aerosols, when they get into the atmosphere, scatter incoming solar radiation back into space. They cool the planet by reducing the amount of energy that reaches the surface. Removing them, even by 1/3, removes that cooling. The atmosphere does not have to be a chemistry lab to be sensitive to this. The effective radiative forcing change was small in absolute terms, but it was concentrated over a small region of the ocean. James Hansen and a team of co-authors published a paper in 2023 in Communications, Earth and Environment that quantified the effect. They found that the IMO 2020 regulation produced an effective radiative forcing increase that is contributing roughly 0.05 degrees Celsius of additional warming per decade. The paper attributes the post-2023 warming acceleration, what some climate scientists are calling the warming pulse, to a combination of this aerosol unmasking, the natural transition out of the 2020 to 2023 triple dip La Niña, and the ongoing background climate warming from continued greenhouse gas emissions. The Hansen paper was controversial when it was published. It has since been picked up and debated by other groups, including the Cornell team that published their own analysis in 2025 and a counterview from Quaglia and Visionnet in Atmospheric Chemistry and Physics in 2025. The numbers are still being argued over, the direction of the effect is not. The North Atlantic is where this matters for what is happening today. The shipping corridors of the North Atlantic are where the aerosol removal was most concentrated. The sea surface temperatures of the North Atlantic have been running warmer than the modern record baseline for almost 3 years now. That warmer North Atlantic is the upstream condition for the Bermuda High. Warm SST anomalies in the North Atlantic favour stronger and more westward extended Bermuda High configurations. When the high extends farther west than usual, it traps warm air over the east coast more effectively, for longer periods, against any incoming weather systems. That is what is happening today. The third precondition is the ENSO transition. The Oceanic Niño Index, which is the operational measure of the El Niño Southern Oscillation, was at minus 0.55 in October, November, December of 2025. By February, March, April of 2026 it was at plus 0.11. The state is officially neutral but trending warmer. The NOAA Climate Prediction Center issued an El Niño watch in May, with an 82% probability of onset in the May through July season. The atmospheric ENSO signal, the part of the system that affects mid-latitude weather patterns, has not fully coupled yet, but it is in the early stages of doing so. Why does that matter for today's pattern? Transition states historically favour amplified ridging east of the Mississippi. The mechanism is partly understood. The redistribution of tropical Pacific heat changes the position of the subtropical jet, which changes where the storm track sits, which changes where the persistent high-pressure features anchor. Whatever the exact mechanism, the empirical record of similar transition states, the Spring 2014 transition, the Spring 2015 transition, and the Spring 2023 transition, all featured amplified eastern ridging at some point during the transition window. The Bermuda High is doing today what Bermuda Highs tend to do during these transitions. Then there is the deeper background, the megadrought baseline that has been the subject of our video from May 12th, and the drought sequel from May 16th. The Williams, Cook and Smerdon paper from 2022 in Nature Climate Change established that the 2000 to 2021 period was the driest 22-year stretch in southwestern North America in at least 1,200 years, based on a tree ring reconstruction going back to the year 800 Common Era. The same paper attributed 42% of the soil moisture deficit to anthropogenic climate forcing. The megadrought is not just a southwest story, it is the foundational state on which all of the current pattern is building. The dry soil that is amplifying today's heat dome is dry partly because of the local synoptic conditions, partly because of the seasonal drought, and partly because of the megadrought baseline that has been depleting the regional moisture for 2 decades. Stack the preconditions. The aerosol unmasking pulse since 2020 has shifted the radiative forcing balance over the North Atlantic. That has warmed the SSTs of the North Atlantic. That has strengthened and westward extended the Bermuda High. The ENSO transition has shifted the storm track and the jet stream in ways that favour eastern ridging. The seasonal drought across the southern plains, the southwest, and parts of the southeast has produced a continental-scale dry land surface. The megadrought baseline has reduced the regional moisture reservoirs that would normally damp short-term events like this one. Each of these alone would not produce today's event. Together, they produce the conditions in which a single ejecting upper trough can amplify a Rossby wave into the configuration we are looking at. The trigger today is the upper trough. The preconditions are everything that has been happening for months, and for decades, to make the trigger this effective. And here is the part that you should sit with for a moment. None of the preconditions are surprises. None of them are unknown. None of them have been concealed by some agency or hidden by some institutional malfeasance. They're all in the published peer-reviewed literature, They are all measured by operational monitoring systems. The drought is in the USDM weekly product. The ENSO state is in the CPC monthly bulletin. The aerosol forcing is in the Hansen paper and its successors. The megadrought baseline is in the Williams paper. The Rossby wave amplification mechanism is in the Petukoff and Kornhuber papers. The pieces are public. The pieces are documented. The pieces have been studied for years. What is novel, and what is in the open scientific question, not in the conspiracy, is whether the combination of these preconditions is changing the operational climatology of the warm season. Whether the days when the wave amplifies into this configuration are becoming more frequent. Whether the climate models that have been used to project the next 20 years are underestimating how often this will happen. The Kornhuber 2023 Nature Communications paper says they are. The next generation of climate models, the CMIP7 suite that is being developed now, will probably try to fix the bias. We will see. For today, the relevant fact is that the preconditions did exactly what the literature said they would do, given the trigger, and the trigger arrived, and the wave amplified, and we are watching the result. Which means today is not actually one anomaly. Today is the moment that 4 anomalies that built separately over months, the drought, the warm Atlantic, the ENSO transition, the megadrought baseline, come together in one Rossby wave amplification. Each one of them has its own face, and those faces are what we're going to look at next. Part 6. The plains outbreak is the trough's other face. The first face you can already see on the radar this afternoon, if you live east of the Rockies, is the plains tornado outbreak. The Storm Prediction Center in Norman, Oklahoma issued a Day 1 convective outlook at 12:46, Coordinated Universal Time today, that contained a moderate risk area covering parts of central and northeast Kansas, southeast Nebraska, and far northwest Missouri. A moderate risk is the 4th tier of the 5-level SPC categorical risk system. It sits just below high risk, which is what gets issued for the kinds of days like April 27th, 2011, when something genuinely historic looks likely. A moderate risk is issued on roughly 4 to 6% of all Day 1 outlook days in the historical record. That is a useful number to hold in your head. 6% of all days. The moderate risk language gets used about 20 days a year on average. Most of those days are in the spring severe weather season, late April through early June primarily. Today is one of them, combined with the fact that the same office on the same day is also looking at an extreme tier fire weather risk on the southern high plains and a moderate risk for flash flooding from the Weather Prediction Center over central Missouri. You have a combined categorical extreme stack that is in the top decile of multi-hazard May days historically. The SPC narrative is worth quoting directly because it tells you what kind of tornadoes the office is preparing for. The text reads, "Supercells capable of producing very large to giant hail and multiple strong to intense tornadoes are most likely from central Kansas and southeast Nebraska into Iowa and northwest Missouri." The hail forecast specifically says very large to potentially giant hail, with diameters of 2 to 4 plus inches. Hailstones larger than 2 inches in diameter, about the size of a hen egg, are roughly the threshold at which you start seeing roof damage on residential structures. Hailstones in the 3-inch range, the size of a baseball, produce broken car windshields and pockmarked siding on every house in the swath. Hailstones in the 4-inch range, softball-sized, produce structural damage to vehicles and can be lethal to anyone caught outside without cover. The tornado language is more specific. Strong to intense tornadoes is the operational vocabulary that SPC uses for tornadoes rated EF2 and above on the enhanced Fujita scale. EF2 is wind speed of 111 to 135 miles per hour, which produces significant structural damage, including the loss of roofs and exterior walls on well-constructed houses. EF3 is 136 to 165, which is the threshold where well-built houses get leveled. EF4 is 166 to 200, which is the level where well-built houses can be swept clean. The SPC is not yet writing EF4 or EF5 language, but the strong to intense vocabulary covers EF2 and EF3. Multiple strong to intense tornadoes means the office is expecting more than one tornado of EF2 intensity, or higher across the outbreak area today. The geography is specific too: central Kansas, northeast Kansas, southeast Nebraska, and northwest Missouri. The cities at risk include Salina, Topeka, Manhattan, Lawrence, and Kansas City, Kansas in Kansas, Lincoln, Omaha, and the Nebraska City Corridor in southeast Nebraska, St. Joseph and the Kansas City, Missouri suburbs in northwest Missouri. The total population under the moderate risk is around 3 million people. Most of that population lives in metropolitan areas where the National Weather Service warning system has been thoroughly drilled and the emergency management infrastructure is in place. Some of it lives in smaller rural communities along the corridor where the storms will travel from west to east through the afternoon and evening. The timing window is also specific. The SPC narrative says robust thunderstorm initiation should occur by 18 to 22 Coordinated Universal Time. That translates to 1 in the afternoon to 5 in the afternoon Central Daylight Time. The earlier cells will fire along the dry line in central Kansas around 1 p.m. They will move east-northeast at about 30 to 40 miles per hour. By 3 or 4 p.m., they will be over northeast Kansas and starting to consolidate into supercells. By 5 or 6 p.m., they will be over southeast Nebraska and the northwest Missouri corner, where the low-level shear is forecast to be strongest. The window from 4 p.m. to 8 p.m. Central Daylight Time is the highest risk window for the strongest tornadoes. There is one ingredient that the SPC narrative flagged as a potential limiting factor: the outflow boundary from this morning's convection in the Missouri-Illinois border region. Outflow boundaries are the leading edges of the cold air that flows out of dying thunderstorm clusters. They can act as focus points for new convection later in the day, or they can act as cap busters that allow new storms to fire that otherwise would not have. They can also screw up the air mass downstream by laying down a wedge of cooler, more stable air that suppresses the afternoon redevelopment. The SPC is watching the boundary's position carefully, because where it ends up by noon will determine whether the moderate risk verifies as written, gets expanded southward, or underperforms because the boundary kills off too much instability. Now here is the question that connects this back to the Wyoming blizzard and the Boston heat dome. Why is this happening today? Why is the SPC looking at a moderate risk over Kansas on the 18th of May? The answer is that the same upper-level trough that is digging into the Great Basin and producing the Wyoming blizzard is the same trough that is ejecting energy out of the Rockies and into the Central Plains. The trough is the western half of the same Rossby wave that we have been talking about for the last 4 parts. The eastern half of that wave is the ridge over the western Atlantic. The trough and the ridge are mechanically coupled. They are amplified together. They cannot persist without each other. The ejecting shortwave from the trough is the trigger for the Central Plains storms. It is pulling warm, moist air northward from the Gulf of Mexico at low levels, while the strong southwesterly flow aloft is moving in cold air at the mid-levels. The temperature contrast between the low-level moist warm air and the mid-level cold dry air is what produces the instability, the convective available potential energy that the SPC narrative is quoting. The Dodge City 12Z sounding this morning showed extreme mid-level lapse rates of 9 degrees Celsius per kilometre in the 700 to 500 millibar layer. That is the steepest mid-level lapse rate you typically see in the plains during a severe weather setup. It supports the very large to giant hail forecast. It supports the strong to intense tornado language. It is what the trough produces when it ejects energy out into a moist warm sector. So when the SPC writes that moderate risk for tornadoes in central Kansas, the office is not just describing today's storms. The office is describing the eastern flank of the same wave that is putting the blizzard warning over Interstate 80 in Wyoming. The wave's western trough is digging into the Great Basin. The eastern edge of that trough is ejecting energy into the plains. The energy is colliding with warm moist air drawn northward from the Gulf, ahead of the trough, by the same broad pressure gradient that is pushing southerly flow up the east coast toward Boston. The southerly flow at the east coast is what is amplifying the Bermuda High and producing the heat dome. The southerly flow over the plains is what is producing the moisture supply for the tornadoes. They are the same flow. In the Severe Thunderstorm Watch number 220, which is currently active until 5 p.m. Central Daylight Time and 6 p.m. Eastern Daylight Time, you can see the eastern footprint of all of this. The watch covers central and east-central Illinois, the northern Indiana corridor through Fort Wayne and South Bend, the Indianapolis metro area, the Michigan corridor through Lansing, and a chunk of Ohio. It includes 9 Illinois counties, 24 counties in northern Indiana, 27 counties in central Indiana, 16 counties in east-central Illinois, plus the southern Lake Michigan marine zones. The list of metros under the watch reads like a tour of the central Midwest: Chicago, Indianapolis, Fort Wayne, South Bend, Lansing, Champaign-Urbana, the entire 65 corridor from Indianapolis north to Gary. The National Weather Service office in Topeka, Kansas, wrote one of the clearer office-level statements in their hazardous weather outlook this morning. The text says, severe thunderstorms are expected after 3 p.m. across north-central Kansas. These storms may form into a line as they move east and southeast late this afternoon and this evening. Very large hail, damaging wind gusts, and a few strong tornadoes are the main hazards. Localized flooding is also a concern, especially if storms persist over areas that received heavy rain Sunday night. A flood watch remains in effect through 7 a.m. Tuesday morning. The office in Wichita, Kansas was even more explicit. Their hazardous weather outlook reads, scattered to numerous thunderstorms are expected to redevelop this afternoon over central Kansas. Some of the storms will quickly become severe and could produce significant severe weather. The stronger storms will be capable of producing damaging winds around 70 miles per hour, up to baseball-size hail, tornadoes, and heavy rainfall. A few strong tornadoes are possible. Stacking the office discussions across the Central Plains, you get the same message in 4 different vocabularies: severe thunderstorms, very large hail, damaging winds, strong tornadoes, heavy rain. The storms will form into a line by evening as the cold front catches up to the warm sector convection. The line will move east through the night and into Tuesday morning. By Tuesday afternoon, the threat will have shifted south into Texas and the lower Mississippi Valley as the front pushes the warm sector southeastward. By Wednesday, the entire pattern will be breaking down as the trough finally moves east and the eastern ridge weakens with it. For today, though, what matters is that the tornado outbreak in the Central Plains is the trough's most visible product. The outbreak is the same wave that put the blizzard in Wyoming. The outbreak is the same wave that is loading the heat dome in New England. The outbreak is the same wave that is pulling moisture northward into the warm sector that is feeding the eastern ridge. One wave, 3 faces visible, and the 4th face is going to come into view when we look at what is happening on the southern high plains, where the drought that we've been talking about for 2 weeks has met the kind of wind that breaks fires open. Part 7. The Extreme Fire Weather Tier and the Drought-Cured Fuel. The Storm Prediction Center maintains 4 operational risk categories for fire weather on its Day 1 fire weather outlook. Elevated is the lowest tier, meaning conditions support the spread of any fires that develop. Critical is the second tier, meaning conditions support rapid fire growth and significant resistance to control. Extreme is the third tier, meaning conditions support explosive fire growth, long-range spotting, and the potential for fast-moving wind-driven fires that overwhelm initial attack. Above extreme, there is no further categorical designation that the SPC uses on its standard Day 1 fire weather outlook product. Extreme is the top tier the office operationally issues. Today, on the 18th of May, 2026, the SPC Day 1 fire weather outlook contains all 3 tiers active simultaneously: elevated, critical, and extreme. The extreme footprint covers the southern high plains. The geography includes the Texas Panhandle, the Oklahoma Panhandle, the eastern third of New Mexico, and the western fringe of Kansas. This is the same corridor that was flagged at the critical level just 2 days ago in our drought sequel video from May 16th. The conditions have intensified. The mechanism is straightforward. The same upper trough that is producing the Wyoming blizzard and the Central Plains tornado outbreak is also bringing strong westerly winds down the backside of the southern Rockies onto the high plains. The air descending off the Rockies adiabatically warms and dries, about 10 degrees Celsius of warming per kilometre of descent, with a corresponding drop in relative humidity, because the absolute moisture content of the air does not change, but the temperature increases. The result is that the surface air over the Texas Panhandle today is going to peak in the upper 90s to 100 plus degrees Fahrenheit with relative humidities in the single digits. The Weather Prediction Center discussion this morning was direct about this. The forecaster wrote, "Strong westerly winds down the slopes of the southern Rockies will meet with dry grounds and low relative humidity to maintain extreme fire weather danger for the southern high plains today, before a cold front brings much cooler air from the north on Tuesday." Then they added, "High temperatures will once again top 100 degrees at the hottest locations over the Texas Panhandle today, before much cooler air arrives tonight." 100 degrees in the Texas Panhandle in May is not unprecedented. The climatology has Amarillo's May average high in the mid-70s. The highest temperature ever recorded at Amarillo in May, since the records began in 1892, is 103 degrees. 100 today, with gusts to 35 to 40 miles per hour and relative humidity in the single digits, places this in the climatological tale of fire weather days for the calendar date. The combination of those three elements, heat, wind, and low humidity, all simultaneously at the extreme end of their distributions, is what produces the extreme tier on the SPC outlook. The fuel state is the part that makes this dangerous. The southern high plains has been in drought for most of the last 6 months. The grass and the rangeland that cover the region are dormant or dying back. The fuel moisture content of the live grass is well below the thresholds that fire managers use to define a receptive fuel bed. CAL fire field samples reported in early May had live fuel moisture content of chaparral in California at high 70s to low 80s%, which is the kind of value that does not normally show up until mid to late June. The same dynamic is operating across the southern high plains. The fuel is cured, it is ready to burn. Add the wind and the low humidity to the cured fuel, and what you have is a high probability ignition day under high consequence spread conditions. The energy release component for the date, which is a national fire danger rating system metric that combines fuel moisture, temperature, humidity, and wind into a single fuel state index, is running at the 90th percentile of historical values for the date across the southern high plains. That is the same metric that has been used in fire weather forecasting for 40 years. 90th percentile is operationally significant. It means the fuel bed is at a level that has historically only been reached on the very worst fire weather days for the date. The NWS Hanford, California office issued a red flag warning earlier this morning for the Westside Hills and the San Joaquin Valley. The text is short and operational. Wind, gusting to 35 miles per hour. Humidity, 15% or less through Monday evening. Highest threat, fast-moving grass fires. Impacts, any fires that develop will likely spread rapidly. Outdoor burning is not recommended. 15 separate red flag warnings are active across the country today, along with one fire weather watch. The geography of the red flag warnings traces the same continental fire weather corridor that we covered in our video from May 16th. The NWS Amarillo office covers the Texas Panhandle and parts of the Oklahoma Panhandle. The NWS El Paso office covers the southern New Mexico zones. The NWS Albuquerque office covers central and eastern New Mexico. The NWS Flagstaff office covers the Arizona High Country and the Painted Desert. The NWS Las Vegas office covers southern Nevada and northwest Arizona. The NWS Sacramento and Hanford offices cover the California Central Valley and the foothills. The corridor runs from California through the Four Corners, through the southern high plains to the Texas-Oklahoma Panhandle. The corridor has been open in some configuration for most of the last 2 weeks. Today it is open with the wind running at the highest gust forecast that we have seen in the corridor this month. Los Angeles is in a separate situation. The NWS Los Angeles Oxnard office issued an update this morning about a late-season Santa Ana wind event materializing across the San Gabriel Mountains. Gusts of 25 to 40 miles per hour have already been recorded, with hotspots reaching 50-plus miles per hour. The Santa Anas are the Southern California cousin of the Diablo winds in Northern California. Both are downslope warm dry winds produced when a pressure gradient sets up between a high-pressure system in the Great Basin and a lower-pressure system offshore. The air is pulled from inland over the mountains and accelerated as it descends through the canyons toward the coast. As it descends, it warms and dries. By the time it reaches the metro area, the relative humidity has dropped into the teens or lower, and the temperature has climbed several degrees above what it would otherwise be. Late-season Santa Anas in May are rare but not unheard of. The climatological Santa Ana season runs from October through April. May Santa Anas happen perhaps once every 3 to 5 years on average, and they happen when a deep upper trough digs into the Great Basin and establishes the kind of inland high pressure that the Santa Anas need. The deep upper trough this morning is exactly that kind of system. The Los Angeles office is concerned about fire weather across the San Gabriels and the Santa Susanas, because the offshore winds are running across a long stretch of warm, dry conditions and over a fuel bed that has been drying out for 2 weeks. The recent fire weather history of the corridor is what makes this dangerous. We talked about the historical fire reference class in our drought sequel video from May 16th, the campfire of November 8th, 2018, which killed 85 people in Paradise, California under a Diablo wind. The Tubbs fire of October 8th, 2017, which killed 22 in Sonoma County under a Diablo pressure gradient. The Marshall Fire of December 30, 2021, which destroyed 1,084 homes in Boulder County under 110 to 115 mile-per-hour gusts at 20 to 25% relative humidity, conditions that exceeded the then-active 15% red flag warning threshold and forced the National Weather Service Boulder office to revisit its threshold structure. The Smokehouse Creek Fire of February 26, 2024, which burned over 1 million acres in the Texas Panhandle, with 500,000 acres in the first 12 hours under 60-plus mile-per-hour winds. The Carr Fire of July 26, 2018, in Redding, California, which produced a fire whirl with EF3 equivalent damage in residential neighborhoods. Each of those fires ignited under wind, humidity, and fuel conditions that were less severe than what is in place today across the southern high plains. The Camp Fire had gusts of high 50s to low 60s. The Tubbs Fire had Diablo pressure gradients producing similar wind speeds. The Marshall Fire was an outlier on the wind end at 110 to 115 mile-per-hour gusts. The Smokehouse Creek event had 60-plus mile-per-hour winds across a 150-mile corridor. Today's southern high plains corridor has 35 mile-per-hour sustained winds with gusts to 45 to 50, single-digit relative humidities, and 100-degree air temperatures over a fuel bed that has been in drought for 6 months. The structural conditions are present. The honest framing, the restraint position that we always try to hold to in this channel, is that today is a high-probability ignition day under high-consequence spread conditions. Today is not yet a fire on the ground. The threat is the conditions, not yet a fire that has started. If you ignite into this fuel bed this afternoon, you get a major event. Whether anyone ignites, whether a lightning strike comes down from the dry thunderstorm potential in the corridor, whether a piece of agricultural equipment throws a spark, whether a downed power line arcs into the grass, whether a discarded cigarette lands wrong, is the contingency. The fire managers in the corridor know this. The Type 3 incident management teams that staff the rural Texas Panhandle and the eastern New Mexico districts are pre-positioned for the contingency. What ties this back to the central thread is the drought. The same dry land surface that is amplifying the eastern heat dome through the soil moisture atmosphere. Coupling pathway we covered in Part 5 is the same dry land surface that has made the fuel bed receptive to ignition today. The Morales 2019 finding, 30% additional likelihood of extreme heat over dry land, is one face of what dry land does. The energy release component running at the 90th percentile over the southern high plains today is the other face. Same drought, 2 consequences, 1 wave, so 3 faces of the wave are visible today. The Wyoming blizzard, the Central Plains tornado outbreak, the southern high plains extreme fire weather. The 4th face is the one that is being held in the soaked Missouri River basins and on the central Missouri flash flood moderate risk that the Weather Prediction Center has on the map for this afternoon. And then there are the other stories of the day, the geomagnetic storm watch, the asteroid that is going to pass closer than the moon tonight, the volcano updates from the Pacific, that are not part of the wave but that some viewers may already be folding into the same framing. We will look at those next. Some are real events. None are connected to what is happening on the wave today. And the distinction matters, because it is the distinction between a story that has a physical mechanism and a story that is being pulled into the same pattern by selective attention. Part 8. The other stories and the open question. The 4th face of the wave is the flash flood moderate risk that the Weather Prediction Center has issued for central Missouri this afternoon. The mechanism is simple. Repeated rounds of training thunderstorms, each one dropping heavy rain over the same corridor, on top of soils that have not had time to drain from the previous round. The corridor includes central Missouri from the Lake of the Ozarks region eastward through Jefferson City and into the St. Louis metro. The slight risk surrounding the moderate risk extends across most of the lower Midwest, from eastern Kansas through Missouri and southern Illinois into western Kentucky. 21 flood warnings are active on rivers across the lower Midwest and the Gulf Coast as of this morning. The Vermilion River at Lafayette, Louisiana is in minor flood. The Calcasieu River near White Oak Park, Louisiana is in minor flood. The Missouri River is in flood at Napoleon, Waverly, Glasgow and Miami, affecting counties from Jackson and Ray through Salin, Carroll, Howard, Chariton, Cooper, Boone, Moniteau, Cole, Osage, Callaway, Montgomery, Gasconade, Warren, Franklin, Crawford, and Washington. The Blackwater River is in minor flood at Valley City and Blue Lick, affecting Pettis, Johnson, Saline, and Cooper counties. The Crooked River is in minor flood near Richmond, affecting Ray County. 10 flood watches are active in parallel. The driver of the flash flood threat is the same warm sector moisture transport that is feeding the Central Plains tornado outbreak and supporting the Eastern Heat Dome. The southerly low-level jet that is pulling Gulf of Mexico moisture northward into Kansas and Nebraska is also depositing that moisture as rainfall on its eastern flank, where the moisture gets lifted over the warm front boundary that runs across central Missouri this afternoon. The training mechanism, the same storms moving over the same corridor repeatedly, is what produces the flash flood scenario. The trough is what is providing the lift. The Bermuda High is what is providing the moisture supply. Same wave, fourth face. That is what is on the wave. The other stories of the day are not on the wave, and the distinction is worth drawing carefully, because it is the distinction between a story that has a physical mechanism and a story that gets folded into the same pattern by selective attention. The first off-wave story is the geomagnetic storm watch from the Space Weather Prediction Center. There is a G1 geomagnetic storm watch in effect for May 18th and 19th, issued by SWPC on May 17th at 16:12 Coordinated Universal Time. The driver is a glancing coronal mass ejection that left the Sun on May 16th. The modelling indicates that the bulk of the ejected plasma will pass just north of Earth, with peripheral interaction producing minor geomagnetic activity. The KP forecast peak is 5.33 for the May 19th 03 to 06 Coordinated Universal Time window. That is barely above the G1 threshold. The potential impacts are weak power grid fluctuations at high latitudes and aurora visibility for the northern tier of the United States. This is a low-end space weather event. It is happening. It is real. It does not drive the atmospheric pattern that we have been describing for the last 7 parts. There is also a notable flare from active region 4436, which produced a C9.7/2N event at 20:53 Coordinated Universal Time on May 17th. The flare was accompanied by a 10-flare radio burst at 370 solar flux units. No coronagraph ejector was identified, so no Earth-directed coronal mass ejection from that event. Region 4436 is the same region that produced the M5.7 flare we covered in our video from May 10th. 10 days later, the region is on the western limb, has rotated past Earth-facing geometry, and is producing smaller flares. The electron flux at greater than 2 MeV energies has been elevated since May 16th, with a peak of 6,120 particle flux units recorded on May 17th. That is well above the 1,000 particle flux unit alert threshold, and is the kind of value that gets satellite operators paying attention. Internal charging on geosynchronous spacecraft is a real concern at flux levels above 1,000 particle flux units. The SWPC has the alert continued. The flux will decay over the next several days as the source decays. All of that is real. None of it drives a Rossby wave. Geomagnetic storms couple to the magnetosphere and the ionosphere, not to the troposphere where weather happens. The energetic particle flux levels we are seeing this week have well understood effects on satellite electronics. They do not have well-established effects on surface weather patterns. The literature on solar troposphere coupling is small, and mostly focused on long-term trends in the 11-year solar cycle, not on individual flare or coronal mass ejection events. The current geomagnetic conditions are an interesting parallel event, not a driver of what is happening on the wave today. The second off-wave story is the asteroid 2026 JH2 close approach. The asteroid is going to pass about 91,300 kilometers from Earth at 2200 Coordinated Universal Time tonight, May 18th. That is 0.24 lunar distances inside the orbit of the Moon, well outside the geostationary ring. The asteroid is between 15 and 35 meters in diameter, traveling at 9.14 kilometers per second relative to Earth. It was discovered 8 days ago by the Mount Lemmon survey in Arizona. We covered the asteroid in detail last night in our video on the sunward blind spot and the planetary defense gap. There is no risk of Earth impact tonight. There is no connection to the atmospheric pattern. The asteroid is on a trajectory that was determined by its orbital elements years ago, computed against gravitational mechanics that have nothing to do with what is happening on the wave. The date coincidence, that the asteroid happens to pass Earth on the same day that the wave is locked in, is coincidence, nothing more. That brings us to the framing that has been circulating on social media this morning about the simultaneity of the events on this date. The framing, sometimes called convergence of energies, sometimes called the Great Alignment, sometimes wrapped in language about cosmic scale patterns or planetary harmonics, claims that the simultaneous tornado outbreak, geomagnetic storm watch, asteroid close approach, fire weather extreme, and heat dome rebuild are evidence of a coordinated process. The argument has gotten enough traction on social platforms today that I think it is worth addressing directly. The honest answer is that there is no physical mechanism that links these events. The energy budget arithmetic settles it. The tidal force from a perfectly aligned planet on Earth's atmosphere is on the order of 10 to the -7 of Earth's gravity. That is 1/10,000,000th of the force that gravity already exerts on the atmosphere every second of every day. The cumulative tidal force from all planetary alignments combined is roughly 4 orders of magnitude smaller than the lunar tide, which is itself too small to detectably affect synoptic weather. The numbers are not in the same room as the effect. The same energy budget arithmetic settles the HARP framing. The high-frequency active auroral research program transmits at up to 3.6 megawatts. The energy contained in a single Rossby wave amplification across the continental United States is on the order of 10 to the 25th power joules. The transmitter cannot inject useful energy into the troposphere at the scale required to lock in a Rossby wave. The geometry is also wrong. HARP transmits upward into the ionosphere, not laterally into the lower atmosphere where weather happens. The UN paper from 2024 in Atmospheric Chemistry and Physics is the canonical reference for the energy budget. The conclusion is that no transmitter at any plausible power level can generate the kinds of large-scale circulation features being observed. Cloud seeding is in the same category. Cloud seeding is a real technology with documented effects in the 5 to 15% precipitation enhancement range under specific conditions where supercooled liquid water is present in clouds that are already going to precipitate. The technology cannot create a Rossby wave. It cannot trap a Bermuda high in place. It cannot generate a blizzard warning over a region that would not otherwise be receiving snow under the same synoptic setup. The mechanism it operates on, augmenting the ice nucleation rate in existing cloud water, is fundamentally local and stochastic. Continental scale temperature anomalies are not in cloud seeding's operating range. The chemtrails framing fails on the aerosol mass budget. The total aerosol mass that commercial aviation emits, even under the most aggressive interpretation, is several orders of magnitude smaller than what would be required to influence a continental-scale circulation feature. The natural aerosol burden over the continental United States during a dry soil period like the present one, wind-lofted dust, biomass smoke, sulfate, is many times larger than aviation contributions. Geographic mismatch is the second problem. Aviation traffic is concentrated in distinct corridors that do not correlate with the location of the Wyoming blizzard or the New England heat dome. The solar-driven framing that current geomagnetic conditions are driving the heat dome or the blizzard fails on the same energy budget grounds. Geomagnetic storms couple to the magnetosphere and the ionosphere through electrical processes that have been studied for decades. The coupling to the troposphere is at most weak. The Marchitelli paper from 2020 in Scientific Reports established that solar seismic correlations exist at the statistical level, but cannot be used to predict individual events. And the follow-up work by Mizuno, Kao and Umeno in Kyoto in 2026 confirmed that the effect is small and limited to seismic activity, not synoptic scale meteorology. The current geomagnetic conditions are a real space weather event. They are not a driver of the wave. What is real, where skepticism is warranted, is the simultaneity itself. The framing on social media that something unprecedented is happening is partially correct in the sense that the specific combination of operational extremes we have today is rare. Where the framing goes wrong is in attributing the rarity to hidden human causes or cosmic scale forces. The actual cause is well understood. The cause is a Rossby wave amplification under transitioning ENSO conditions with anomalous soil moisture and aerosol-elevated background temperatures. The cause is the kind of cause that climate science has been describing for decades. The science is open. The Kornhuber paper is public, the Williams paper is public, the Hansen paper is public, the data feeds from the National Weather Service are public, nothing is hidden. The conspiracy framings explain a phenomenon that does not need the conspiracy framings to explain it. The actual explanation is in the literature, and the actual explanation contains the genuinely open question, which we will close on. The Kornhuber 2023 follow-up paper in Nature Communications, the one we mentioned in Part 4, made an argument that has not been fully absorbed yet by the operational forecasting community. The argument was that the climate models that are being used to project the next 20 years of warm season weather are systematically underestimating the frequency and intensity of resonant Rossby wave configurations, like the one driving today's events. The reason is that the models have structural biases in how they represent the upper-level jet stream. They tend to be slightly too zonal, too west to east, and do not amplify the waves enough. When you compare model output to observations over the recent decades, the observations show more amplification and more synchronized extremes than the models predicted. If the Kornhuber 2023 argument is correct, and the empirical evidence so far supports it, then the days like today are happening more often than the climate projections said they would. The pattern of events we have on the screen this morning, 5 operational extremes simultaneous, on one wave, on a single calendar date in May, is not a once-in-a-decade event in the new operational climatology. It is more common than that. How much more common is the open question? The models say once every 10 to 15 years. The observations of the last decade say closer to once every 3 to 5 years. The disagreement between models and observations is what makes this a research-active question, not a settled one. What this means for the forecasts that lead into June, July and August this summer is that the configurations that produce concurrent extremes, the simultaneous heat dome, drought, fire weather, and severe weather days that historically were operationally rare, are very likely to repeat. The Climate Prediction Centre's June through August 2026 outlook continues to favour above normal temperatures across most of the country. The El Niño watch is in effect for the summer transition, with 82% probability of onset by July. The transition state is one of the conditions that historically favours amplified ridging. Once the El Niño signal couples atmospherically, the wave configuration that we have today may become a recurring summer feature rather than a transient mid-May event. And the warning systems were not designed for what comes next. The National Weather Service is built around individual hazard categories: severe weather watches, fire weather outlooks, heat advisories, winter storm warnings, flood warnings. Each category has its own product. Each product has its own audience. Each product flows out to different sectors of the public: broadcast meteorology, emergency management, transportation, agriculture, healthcare. The simultaneity of 5 categorical extremes on a single calendar day strains the communication system. The audience under a heat advisory in Boston is not the audience under a blizzard warning in Wyoming. The audience under a tornado watch in Indiana is not the audience under a red flag warning in the Texas Panhandle. Each office is talking to its own region. No one is talking about the wave that is doing all of it. This is the structural problem that today's event exposes. The atmosphere is doing one thing. The warning system is communicating it as 5 things. The audience hears 5 different stories from 5 different agencies and may or may not connect the dots. The dots are connectable. The connection has a physical name: quasi-resonant amplification, wave number 5 to 7 Rossby resonance, low phase speed wave packet, mechanically coupled trough ridge configuration. The physical mechanism is in the peer-reviewed literature. The connection is not hidden. It is just not built into the communication architecture of the National Weather Service. And if the days like today are happening more often than the climate models predicted, the communication architecture is going to have to catch up. The audience is going to need to understand what a Rossby wave is. The audience is going to need to understand that one wave can produce a heat dome and a blizzard at the same time, on opposite ends of the same continent on the same calendar day. The audience is going to need to know that the heat under the eastern ridge and the snow over the western trough are 2 faces of one configuration. The audience is going to need to be able to think of the atmosphere as a system rather than as a series of separate stories. That is the audience we have been building on this channel for the last few months. The reason that the drought primary from May 12th landed, the reason that the multi-hazard May storm setup from May 13th landed, the reason that we keep returning to the same studies, Williams, Cook, Smerdon 2022, Hansen 2023, Han 2021, Kornhuber 2020 and 2023, Morales 2019, is that those studies are the architecture that explains what is happening when the atmosphere does what it did this morning. The audience that watches this channel does not need to be told that a heatwave is hot. The audience needs to be told what is driving the heat wave, why the heat wave is on the same wave as the blizzard, and what the configuration means for the rest of the warm season. The pattern breaks down on Wednesday afternoon when the cold front arrives. The eastern ridge weakens, the wave finally progresses east. The Bermuda High retreats offshore. The wave's amplitude drops back into the normal range. By Thursday, highs in the northeast are forecast to be 15 to 20 degrees cooler than Tuesday's peak. The Friday through Memorial Day weekend forecast is for cool, near-seasonable temperatures. The pattern is over by the holiday weekend, but that is just this pattern. The configuration that produced today's events is one that the literature says is becoming more common. The next time the wave amplifies will be on a different date with different specific verifying conditions. The eastern ridge may park over the southeast instead of the northeast. The western trough may dig into the northern Rockies instead of the Great Basin. The simultaneous extremes may be tornadoes plus heat plus drought plus flooding without the snow component, or they may include the snow component if the timing is in a transition month. The combinations will vary. The mechanism will be the same. If you have watched this channel for the last 6 months, you have already watched the mechanism produce concurrent extremes several times. The bicoastal heat dome from May 8th was an early version of today's configuration with Phase 1 spatial signature, coast-to-coast simultaneity. The Phase 2 inland migration from May 9th was the same wave moving its anomaly westward and upward into the high plains. The multi-day pattern setup from May 13th explicitly forecast today as the verification day for the eastern rebuild. The fire weather corridor from May 16th was the same trough southern flank lighting the southern high plains. The Everglades on fire from May 11th was a different wave doing a similar trick on Florida specifically. Today's event is the most clearly visible instance of the mechanism, because today's spatial signature includes a blizzard warning that nobody can ignore alongside an East Coast heat dome that everybody can feel. So what do you do with this? What do you do with the knowledge that the atmosphere is doing something the models did not fully predict, on a calendar date that historically had not produced this kind of simultaneous extreme combination? The honest answer is, you watch. You pay attention to the pattern when it forms. You learn to recognize the signature of an amplified Rossby wave on a 500 millibar chart, which is something that any weather enthusiast can do with 20 minutes of attention to a single map product. You learn to ask, when the local forecast says it is going to be unusually hot or unusually snowy, what the synoptic pattern is doing on the larger scale. You learn that the heat on the East Coast in May is not separate from the snow in Wyoming in May, when they are happening on the same calendar day. You learn to think of the country as a connected weather system rather than as 50 separate states. And you start to plan for the configuration recurring, not because every day will be today, but because the days that are like today are becoming more common, and the next one might be on a different combination of extremes, on a different date, with different specific verifying conditions. The Climate Prediction Center summer outlook continues to favor above normal temperatures across most of the country. The El Niño watch is in effect through the summer. The atmospheric ENSO signal is not fully coupled yet. The wave configuration that we have today is one of the configurations that can produce the kinds of concurrent extremes that we have been seeing more often than the model said we would. The next pattern is on the horizon. It might be a week away. It might be a month away. It will not be longer than that. The cold front arrives Wednesday afternoon. The heat dome retreats Wednesday night. The Wyoming snow tapers off this evening. The Plains tornado outbreak peaks between 4 p.m. and 8 p.m. Central Daylight Time this afternoon. The fire weather corridor will get the cold front Tuesday, and conditions will moderate Tuesday night. By Friday, the pattern is over, and the country is back to seasonable weather for the holiday weekend. The next configuration is waiting. The atmosphere did something today that nobody alive has ever seen at exactly this combination of intensities. 5 simultaneous categorical extremes, 1 wave, 1 calendar date in May, the central thread of 1 Rossby resonance running from the Pacific Northwest to the Western Atlantic. The patterns that produce events like this are happening more often than the models predicted. The patterns that produce events like this are arriving earlier in the year than the models predicted. The patterns are real, the mechanism is real, the literature describing them is real and public. None of it is hidden, none of it is unknown. The only thing that is unknown is how many more days like today are going to happen this year, and how many of those days are going to be more amplified, with stronger extremes, on more impactful dates. The wave that did this is going to break by Wednesday night. The next wave is already in the data, waiting to come together. We will know by next weekend whether the pattern wants to lock back in. The first signal will be the position of the Bermuda High and the depth of any new trough digging into the Great Basin. If both come back together, the pattern is loaded again. If they do not, we get a couple of weeks of seasonable weather before the next attempt. Either way, what we are watching is not a one-off event. What we are watching is what the atmosphere is becoming, and the days like today, with all their simultaneity and all their amplitude and all their record threat language out of the operational offices, are not going to be the last of this pattern. They are going to be the early instances of the new normal. There is one more piece of context worth holding before we close, because it cuts to why this matters past the meteorology. When the Kornhuber 2020 paper looked at the crop loss numbers associated with wave number 5 and wave number 7 resonant events, the regional losses were on the order of 11% for the worst configurations. That 11% does not sound like much when you read it on a page. Translate it to dollars and to food security, and the number changes its meaning. The major breadbasket regions of the Northern Hemisphere, the United States Midwest, the European Wheat Belt, the Black Sea Grain Corridor, the Chinese North Plain, the Indian Indo-Gangetic Plain, together produce more than half of the world's caloric supply of staple grains. An 11% regional reduction in 2 or 3 of those breadbaskets simultaneously in the same year is the kind of food supply event that the international grain trade was not designed to absorb. The 2020 paper specifically called this out as the policy-relevant finding. The 2023 follow-up tightened the case. The models were missing the concurrent extreme risk. The observations were showing more synchronized failures than the models projected. The implications for global food security are not abstract, they are operational. What we are watching this morning in the United States is one wave number on one continent. The same kind of pattern can produce concurrent extremes across continents when the resonance is broader. The literature documents this clearly. The summer of 2010 saw a concurrent Russian heat dome and Pakistani monsoon flooding, driven by a single wave number 7 configuration. The summer of 2018 saw concurrent extremes across Europe, North America, and East Asia driven by another wavy number 7 year. The summer of 2022 saw the same. The patterns are real and they are repeating. The question of whether the models are catching up, whether the CMIP 7 generation of climate models that is being developed for the next IPCC assessment will reproduce the resonance behavior more accurately, is the question that the modeling community is wrestling with right now. The early indications are that the new models are doing better than the previous generation. They are not doing perfectly. The gap between model and observation is narrowing, not closing. So there is a longer arc here, and the arc is not finished. Today's pattern is one instance in a longer sequence that is going to keep happening, will keep being documented in peer-reviewed literature, and will keep producing the kinds of operational anomalies that we have been watching this month. The drought, the heat domes, the multi-hazard May storm setups, the fire weather corridors, the simultaneous coast-to-coast extremes, all of these have a common driver, and the driver has a name, and the name is showing up in operational forecasts and in research papers with increasing frequency. The mechanism is no longer hidden. The names are public. The literature is open. The forecasts are improving even if the projections are still lagging. Tomorrow, when the records fall and the broadcast meteorologists tell you the story of the heat, you will know something that almost nobody else watching the broadcast will know. You will know that the heat is one face of the same wave that put a blizzard warning in Wyoming this morning. You will know that the wave is in a configuration that the climate science literature has been describing for the last decade. You will know that the configuration is happening more often than the model said it would. And you will know that the question of what comes next, after this wave breaks Wednesday night, is the question that nobody has the answer to yet. The cold front arrives. The pattern resets. The atmosphere goes back to looking quiet. And then, sometime later this summer, the wave amplifies again. And the next time, it might not look anything like today. The only thing it is guaranteed to share with today is the mechanism. And the mechanism is one we are going to be seeing a lot more of. That is the open loop. That is what is far from over. The wave that did this today is not the last wave that will do this. And the configuration we are watching is the early version of what the atmosphere is allowed to do in mid-May now. The honest framing is the one we have to leave you with. The science is open, the mechanism is known, the pattern is happening, and the question is not what the atmosphere did today. The question is how many more days like today the rest of this year is going to contain. And the answer, when it arrives, will arrive the same way today's pattern arrived, quietly, on a forecast model 5 days in advance, in language that the operational officers will use as carefully as Boston used theirs this morning, close to the maximum relative to climatology. That phrase is going to show up in more discussions before this year is out. Listen for it.